Better if I Is it better if I ask on the chat or?
Okay, the meeting is being recorded. So tell me, what is there any other question? So what is the variable a in this problem? I think a is the link length.
No, for problem question number 3, there is another a given.
Oh, don't worry about question number 3. That question number 3 and 4 about is a Lagrangian, right?
Yep.
Yeah, I would solve that problem. So don't worry about it. Just do forward kinematics, inverse kinematics, and next time when you come, give me all the homogeneous transformation matrices, and I will show you how to set up the Lagrangian, and we will solve the part 2 and part 3 here. Yeah.
And there is a cylinder. Is this a cylinder, the first joint?
Yes, the cylinder is a
If it's
first.
the first joint.
It's a Revolute, prismatic Revolute robot. Revolute RPR.
No, I'm talking about the joint.
Which joint are we talking about?
This whole thing. This thing is a keyboard. This thing is a cylinder. We need a radius to find the moment of inertia.
Oh, yeah, you can. Okay, yeah, I understand. You can. So the moment of inertia for that guy would be ml. Okay, I'll give you that value.
Okay.
You don't need moment of inertia to find out forward and inverse
No,
kinematics.
I have them for the Lagrangian.
I can't find the file. Yes, the mass m is the same for each segment of robot, but you don't have to worry about it because I would work out the kinematics. I mean, I will work out the kinetic energy and Lagrangian and the other part. So next time when you come, yes.
So for T1, T2, and T3,
Mm-hmm.
are we saying that that is beta 1, beta 2, and beta 3? Or what is T1, T2, and T3? What
Okay.
is that?
So this is the inverse kinematics for assignment 2.
Right.
And I used Matlab to solve the inverse kinematics problem.
Right.
And what I'm suggesting is rather than reinventing the wheel, start with this script,
Right.
modify this script so that it will give you inverse kinematic solution for assignment, the first part of assignment 5.
So I guess I should restate my question is for this new assignment, what would T1 or T1 through 3 represent?
The joint variables. Joint variables.
The joint variable. Okay.
And you do, so you have 3 joint variables, just like this problem. The first joint variable is angle theta 1.
Correct.
Second joint variable, since it's a prismatic joint, you have the distance d2.
Correct.
And third joint variable, again, it's a revolute joint, so you have theta 3. Any other questions here? Okay, and my suggestion / request to the students who finish the robot is help your classmates because some of the students are really struggling in getting things working. So it's okay to get help from your friends. So, and of course, I'm here to help you. But it's okay if you think you can't work with HM10. If you wanna go and get HC05, that's fine too. If you want to buy discrete servos, that's fine too. You can buy the hardware from Amazon for 10-15 bucks and get your robot working. Alternatively, if you want to swap the Arduino with an ESP, I can give you an ESP. But then you need to make sure that your ESP, you enable the Bluetooth on your ESP so you can talk to ESP32. Okay, so I'm gonna start today's lesson. Okay. So in last class, I talked about logarithms. And then I kind of give you an idea how Laplace transform is similar to logarithms. So in today's class, what I'm going to do is I'm going to restate the obvious So if you have a huge number, so 1 into 10 to the power 5, this is a huge number that needs to be multiplied with another huge number. This is going to be a very big number. And this computation will take a lot of time. So alternate approaches, rather than performing multiplication, you take the log of these numbers. So you basically perform a log operation. You perform another log operation, and the multiplication in the algebraic domain becomes the addition in the log domain. And what you get is, since these numbers are going to be small, so let me say 1235 plus maybe 2.123. So I'm guessing. So the addition is very quick. And then whatever results that you have, what you do is you find inverse log. And once you find the inverse log, that gives you this huge number that you are looking for. That is the advantage of logarithms. So Laplace transform does the exact same thing. And I want you to remember only this. So the use of Laplace transform in robotics is to solve differential equations of motion for the robot. Now, what does that mean? So if you think about it, there is something called as time domain, and there is something called as the Laplace domain. In time domain, the variable is t. In the Laplace domain, the variable is s. And only thing that I want you to remember, I will give you the definition for a Laplace transform. I will work out some problems from Laplace transform, but we are not going to solve Laplace transform by hand. So think about it. You have something called of x of t. In Laplace domain, you have the variable x of s. In the time domain, the independent variable is t. In the Laplace domain, independent variable is s. If you take the derivative in time domain, it becomes s multiplied by x of s. If you take the second derivative, it becomes s square x of s. If you take the third derivative, it becomes, can someone tell me what would it become? S cube x of s. Now, what is the advantage of this transformation? And I just want to tell you what does this transformation do. Laplace transform takes a differential equation. Laplace transform takes the differential equation and converts that into an algebraic equation. And what we do is we solve this algebraic equation. So I'm going to say LP, which is the Laplace transform. We solve this algebraic equation and then use inverse Laplace transform. So inverse Laplace transform and find the solution of differential equation. Everyone understood this? So this is exact same thing as logarithms. Instead of multiplying using log transformation, we perform addition. So instead of integrating by using Laplace transform, we perform addition. So let me tell you how this process works. Imagine you have a differential equation mx double dot plus kx is equal to 0. Now this equation is in the time domain. Why is it in the time domain? Because your variable, the dependent variable, is x of t, where time is the independent variable. So time is the independent variable. So if I want to solve this differential equation, what I need to do is I need to solve it either using numerically, or I have to solve it using some sort of analytical technique, or the exponent of matrix that we talked about. How does it work in Laplace transform? Now, please note, m is a constant, so it's going to remain as m. Check x dot. X dot is over here. That in the time domain, you have x double dot. In the Laplace domain, it becomes s square x of s. So what you have is, you have s square x of s plus, then you have k. K is a constant. So x here becomes x of s over here. And typically what you have is, you will have some other external function or external force u of t. And I'll tell you what that means in just a second. So u of t will become u of capital U of s. So this becomes u of s. Now, can you see in this entire expression, I can take x of s outside. So my equation becomes ms square plus k is equal to u of s. Do you agree with me? Now, this guy is the output. This guy is the input. And what do I mean by output and input? So let me show you in the physical system how these things happen. So you have stiffness K, you have mass M, and you have an external force U of T acting on the system. So if you look at this expression, you have mx double dot, which is the inertia force, kx, which is the spring force, and summation of forces is equal to the external force that is applied. So after you take the Laplace transform, what you have is, you have a very simple expression, x of s in the parentheses ms square plus k is equal to u of s. And this u of s, or for that matter u of t, this u of t could be sine omega t, which would be a sinusoidal excitation, or it could be a ramp function, or it could be a step function. So u of t could be any type of input. So what I'm going to do is, now I'm going to take x of s, which is the output, and I'm going to have divide by u of s, which is input. And what I have here is ms square plus k. So what it means is, somehow, if I'm able to solve this expression, I know the solution for x of s. And to be honest with you, we will not solve this expression by hand. The best way to solve this type of expression is using Matlab. So here is what we are going to do when we talk about studying Laplace transforms. Laplace transform is used to transform differential equations into an algebraic equation. And when you have an algebraic equation, and when you take the Laplace transform of input, Laplace transform of output divided by input, it is called as the transfer function. So transfer function is Laplace transform of output divided by Laplace transform of input. And you will see transfer functions are super important when we study the dynamics or dynamics of robots, or for that matter, any system dynamics. One thing to note, Laplace transform can be only applied to linear system, linear constant coefficient systems. What does that mean? It means you cannot use Laplace transform to solve an expression mx double dot plus kx plus k2x cube is equal to 0. Laplace transform cannot be used to solve this equation because this is a nonlinear function. So if you have a nonlinear equation, Laplace transform cannot be used. Also, imagine a case that mass is changing. Say, for an example, you have a rocket and the fuel is being consumed. So the mass of the rocket is changing as time goes from 0 to say 10 seconds or 15 seconds. Laplace transform cannot be used when the mass or the stiffness or any other parameters are changing. So Laplace transform cannot be used if your equation is something like this. So please note here mass depends upon time. The stiffness depends upon time. So they are changing. Laplace transform cannot be used. So what is the formal definition of Laplace transform? Laplace transform of a function f of t. Laplace transform of a function f of t is the integration of 0 to infinity e to the minus st f of t dt. So please note what you do is this s is called Laplace transform variable. And I can actually work out an example to find, but to be honest with you, I'm not gonna ask you to find Laplace transform by hand, but let me just work out a Laplace transform. So let's find out the Laplace transform of a step function. So this is a step function. So this is time. Step function is a constant function at constant magnitude. So if you look at time and if you look at s at time t is equal to 0, what you have is so let me solve this problem. So Laplace transform of f of t is equal to 0 to infinity f of t e to the minus st dt, and f of t is nothing but a. Can you see as time goes from 0 onwards? So a f of t is equal to a. So what I would do is I would substitute 0 to infinity a e to the minus st dt. When I perform the integration, I need to integrate e to the minus st. A is a constant that comes out, and I have the answer to this integration is e to the minus st divided by derivative of minus st, which is minus s. Limits are 0 to infinity. So this becomes a. I will take minus s here, and then I would have e to the minus s infinity minus e to the minus s multiplied by 0, and this gives me a of s. So if you look at the Laplace transform of this function, so f of t is equal to a. The Laplace transform is given by a divided by s. So what does that mean? So let me set up this problem. That way you will understand So consider a problem. What we have is we have a spring mass system. The spring has stiffness 5. The mass is 1 kilogram and it is subjected to a step input. So UT is the step input wherein the step is 2 units. So this is the step input. So 2. So if you look at the equation, this equation is going to look like, so 1 x double dot plus 5x is equal to 2. And what I need to do is I will have to solve this equation. So we looked at this equation earlier. X of s divided by u of s is equal to 1 divided by s square plus 5. Look at this expression that we just derived here. M s square plus 5. M is 1, k is 5. So u divided by s. Now, if you look at x of s, that is what we want to find out. U of s is a step input. The Laplace transform, so x of s is equal to 1 divided by s square plus 5 multiplied by u of s. U of s is the Laplace transform of input, and the Laplace transform of input is going to be 1 divided by s square plus 5 multiplied by, you would have a, which is 2 divided by s. So what you have now is you have this equation s square plus 5 x of s. If you take the inverse Laplace transform of this expression, if you take the inverse Laplace transform of this equation, the variable s would get converted to variable t. So once you take the inverse Laplace transform of this expression, 2 divided by s square plus 5, that's what I have, right? 2, okay. 2 divided by s square plus 5. If you take the inverse Laplace transform of that expression, you are going to get an expression in x of t. And that expression is going to be the solution of this differential equation. Everyone understood this? Now, some of you may ask me, how is this done? This should be, hopefully, this was covered in your differential equation class. And as you can see, there is partial fraction expansion, and there are other techniques wherein basically you split this, and then there are Laplace transform pairs. So there is a table that you use and go back. But we don't do that. We are lazy. We are going to use Matlab. Everyone understood this? Are we good with Matlab? Okay. The only issue that I want to tell you is the tricky part is how to take into account initial conditions. So initial conditions. And I will explain it to you with the Matlab script. How would you encounter, or how do you compensate for initial conditions? What that means is, since this is a second order equation, remember x double dot, second order. How many times you have to integrate? 2 times you have to integrate. 2 times you have to integrate means you need 2 constants of integration. And those are the initial conditions. So you need to supply initial displacement x of 0, and you need to supply initial velocity. So you need to supply initial displacement and initial velocity. So these 2 conditions need to be supplied, and that you have to incorporate in Laplace transform. Are you with me so far? Any questions? Any questions here before I go on to the Matlab? So what I want to do is, I want to I want to solve an expression, a simple expression. So this is the problem that I want to solve, and this is the problem we'll actually solve. So consider a spring mass damper system. So you have a spring, you have a damper, and you have a mass. And so say your mass is 0.8 kilograms. You're not able to see. Huh? Oh, sorry. Yeah, I'm writing. Oh, yeah, sorry. So 0.8 kilogram. I was just looking at the differential equation that I wanted to solve. Then 3 plus, okay. So damping value is 3 and the spring value is 8. So mass is equal to 0.8. K is equal to 8. This is 8 kilogram, 0.8 kilograms, Newton per meter, and C is equal to 3 Newton second per meter. Because this is assumed to be a viscous damping, so this is the damping coefficient, and on this there is an external force F of t, and that F of t is equal to sine t. So if I want to write down the differential equation of motion, it is going to be 0.8 x double dot plus 3 x dot plus 8 x is equal to sine t. And I'm sure you have solved this differential equation in differential equation class. Have you? Okay. I'm sure you took that class, right? So now what I want to do is, I want to solve this equation using two techniques. One technique is the analytical technique, and the other technique is Laplace transform. So now if you go to the canvas, there is a Matlab script on the Laplace.m. So please download that script, and that script actually solves this differential equation. So I'm going to now switch to Matlab. So I'm going to share my Matlab screen. So now you should be seeing my script, and I would explain to you step by step what does this script do. So this is the Laplace example. The first, so there are two things that are happening. I'm solving the differential equation numerically by numerical integration. I'm solving the differential equation analytically in the closed form, and I'm solving the differential equation using the Laplace transform. And this differential equation solution should be the same no matter how I solve it. So what I want to do is, let me explain first part. I want everyone to focus on line number 19. So can you see on line number 19, what I have is, I have this differential equation. The only difference here is the external force is 0. So X analytical, I'm using the built-in Matlab function dsolve to solve this differential equation. And this differential equation is 0.8 d2x. d2x is the x double dot plus 3 times dx, which is x dot, plus 8 times x is equal to 0, which is the right hand side. And the initial conditions are the displacement x of 0 at time t is equal to 0, x is equal to 1, at time t is equal to 0, dx, which is the velocity, is 0.5. So this is the analytical solution. And then what I'm doing is, I'm plotting the analytical solution, the solution of analytical solution. Now next part, is what I'm doing is I'm actually solving the differential equation using Laplace transform. And for Laplace transform, I'm finding out the symbolic variables. I'm determining or indicating symbolic variables, the Laplace transform variable S, the time variable t, and the capital Laplace variable x. And then I'm defining an external function f sine t because I want to solve the forced problem later. So d1x, as you can see, d1x is x dot. X dot is actually s times x. So I just said, x dot is equal to s times x. But this -1 is nothing but the initial condition on the displacement. So as you can see, there is this initial condition that we need to take care. So the initial condition here is 1 and 0.5. So I need to supply this initial condition. So this is the initial condition on displacement. d2x is s at d1x minus 0.5. This is the initial condition on velocity. So as you can see, this d1x is substituted here. So you are gonna get s square multiplied by x minus 1 multiplied by s minus 0.5. This is going to be the expression for d2x. And then what you do is you can actually solve this equation. And please understand, this becomes a very simple algebraic equation. And once you find the solution, here you find the inverse Laplace transform of the solution. And then you can actually plot this. And the last part is we are trying to solve the same expression numerically. So when we try to solve it numerically, the differential equation needs to be written in state space that we talked about in last class. So you have the derivative of displacement, which is the velocity. Derivative of velocity is nothing but minus k divided by x minus c divided by m multiplied by x num2, so which is the velocity. So what you can do is you can run this code and then it will find out these solutions, and you will see that these solutions, they match fairly well. So this is the displacement computed from the numerical solution. This is the velocity that is computed from the numerical solution. This is the displacement that is computed using the analytical solution. And this is the displacement that is calculated using the Laplace transform solution. Everyone understood this? So you can use this script to solve any problem. Now, the advantage of Laplace transform is not just solving the differential equation, but Laplace transform enable us to find something called as transfer functions. Transfer function is nothing but the Laplace transform of output divided by input. So if you are with me, what I want to do is, at this point, I want you to open Simulink. So new, and then so new, I'll just click here Simulink. So I want you Simulink. Does everyone remember what I did a minute ago? I wrote the Laplace transform of this system, mx double dot plus kx is equal to, say, f of t. When you take the Laplace transform, this becomes ms square x of s plus k x of s is equal to f capital F of s. So x can be taken common outside. So this becomes ms square plus k x of s is equal to f of s. This is output. X of s is output and f of s is input. Just look at the equation that I wrote on the whiteboard. So the transfer function is Laplace transform of output divided by Laplace transform of input. So this is transfer function. And this is going to be nothing but 1 divided by ms square plus k. So with this information, with this knowledge, what I want to do is I want you to open Simulink. Now, when you go to Simulink, yeah. Zoom screen. Oh, yeah. Yeah, I need to. You're right. I need to update Zoom screen. So, yeah. So you should be able to open Simulink. And in Simulink, this canvas opens. And if you look at this canvas, I want you to go to the library browser. And in library browser, I want you to go to commonly used blocks. And let me see if there is continuous. And then you will see that there is, I'm looking for transfer function. Yeah, so can you see this transfer function block? I have to update the. So please, students who are online or Zoom, go to continuous Simulink library browser, grab this transfer function block and drag and drop onto the canvas. And once you have this transfer function block, double click on this transfer function block. And what you see here is you have some numerator coefficients. You have some denominator coefficients. Let me give you value of mass. Say mass is equal to 5 and stiffness K is equal to 10. So mass is equal to 5 and K is equal to 10. So your denominator coefficients are going to be 5. Please note, this equation is something like 5s square plus 0s plus 10. So in the denominator, you would have 5, 0, 10. So, and if you see now, you should be seeing the transfer function, which is 5s square plus 10. Are you with me so far? Online students, any question? Are you able to get the transfer function set up? Screen over to side. I am sharing, yeah.
You just share your screen, they can see everything. So if you click into anything, they can see without you have to keep updating it.
Okay, I will share the whole everything.
And then they should be able to see everything.
Yeah. So now you should be able to see my screen with 5s square plus 10. This is the transfer function. Everyone understood this? Now solving a transfer function in Matlab is super easy. So imagine that if my input is a sinusoidal input. So if my input is like a sine wave, what I can do is I can go on to the library and then I can go to sources, and then what I can do is I can look at sine wave. So grab sine wave, drop over here, and now what you have is, so basically you have this sine input. Again, if you want to see what it looks like, can go on to the commonly used blocks and use the scope. So now think about it, what Matlab is doing. All the mathematical jugglery that we did in M script, M file, all is taken care. I can supply input. It could be a sine function. It could be a step input. It could be a ramp input. I can just provide that input to this box, this transfer function blocks, and I would get the solution of that equation. Everyone understood this? So if you click on this, let's look at what is the magnitude of the sine wave. Amplitude is 1, frequency is 1. So I run this and look at the scope, and that gives you the solution. Now, there is something I want to show you, and that is actually an important concept. So now what I want you to do is,